God, Hillary, do you know how to punch? Let's get it. Let's get it. Let's get it. Beat him up. Beat him up. Oh, shoot. So sorry. Supposed to be doing an explainer video. Alrighty. Sorry about that. Welcome back, Physics 40B, to another explainer video. This is number 15.75. And basically, we're going to do that. We're going to get right into this problem. So here's the question. A block on a frictionless table is connected as shown in figure 15.75 to two springs having spring constants K1 and K2. And it's asking us to find the expression for the block's oscillating frequency F in terms of frequency F1 and F2. And at which it would oscillate if attached to spring 1 and spring 2 alone. So basically what it's asking us to do is basically make this diagram as if it was just one spring but having two spring constants. So we're going to put both of the spring constants together and act if it's one spring and then figure out the equation for the frequency. So to start off, we need to do a free body diagram. So let's get right into it. As you can see, DJ Khaled says this is the key to success. So this is our free body diagram right here. So this is the wall. This is spring 1 and this is spring 2, and then this is the mass. So spring 1 has K1, spring 2 has K2, spring 1 has delta X1, and spring 2 has delta X2. So the total delta X is going to be X1 plus X2. Pretty simple, right? We also know that the F net is 0 because it's a free body diagram, and I think this is static, so I'm not sure, to be honest. So, and then we also know, so this is all we really need from this free body diagram. So we're going to draw another one as if it was just one continuous spring with our new displacement. So displacement X is, I just rewrote it again, displacement X is just equal to X1 plus X2. And we have our mass, and then we have our force. So if this force is applied to this system right here, it would apply evenly. So this at this joint, it would feel the same force. At this joint, it would feel the same force here and here. It would all feel the same force. And we're going to use these two equations up here. So the frequency is equal to the square root of the spring constant divided by the mass. And I found that equation right here on Google Image. Right here, I used this one. And then this one is just a rewritten form of that, solved for K. Cool. So also, we know that the force of a spring is equal to the spring constant times the displacement X. So here we have the force is equal to the constant of the second spring times the displacement, and that's also equal to the constant of the first spring times the displacement of the first spring, because the forces have to be equal to each other. So from here we can just write this equation, net force is equal to the constant net times X, and this X is again X1 plus X2. So solving for this X, we're just going to divide this side by Kn, and we get F over Kn, and then that's equal to, we know X is equal to X1 plus X2, and X1 up here is equal to K and then F. There's a lot of rewriting. So you basically, to get X1, you divide this side by K, and you divide F by K, so you get F over K1. And then for X2 right here, you divide X2 by K2, and you divide F by K2, and you get this. So now we're left with this right here, this right here. It's confusing, I know. So since we have an F on top on each of them, we can basically just get rid of it and just set it equal to 1. And then we're left with this one now. And then from here, I kind of got stuck and I had no idea how to simplify this. So then I went on YouTube and I found a similar example right here. And he basically just combined them to look like this. I'm pretty sure I could have done it, but my algebra sucks. So anyway, so K effective is what he called it. And then we're just going to do K1 times K2 over K1 plus K2. And then using the equation, this one, so we know K is equal to the frequency squared times mass. So we're just going to use that. We're going to use that right here. So this K is equal to the frequency squared times the mass, and this K is equal to frequency 2 squared times the mass, and then down here same thing. So from here we can just factor out one of the masses over here from the bottom and then cancel out one of the mass, and then we're just going to rewrite this K in the equation. Alright, I know it's a lot. So here's what this new equation looks like. So K is equal to the mass times F1 times F2, all those squared, over F1 squared plus F2 squared. We're going to plug it into this equation. K is equal to that, so we're going to plug this equation into this K. This mass and this mass will cancel, and we're left with this final equation. The frequency is equal to the force, or to the frequency 1 squared plus frequency 2 squared over frequency 1 squared plus frequency 2 squared. And that's literally it. Cool, thank you.